Good. All right. Hello, everyone. So welcome to lecture 4. For all of you who survived the first 3 lectures. So great. So what we're going to do today is basically cross the bridge between array structures and topological recursion. And the cool thing is that the bridge is also the origin of topological recursion. So we'll basically talk about where it comes from, why is that an interesting formula, and why it calculates pretty much the same thing as array structures. So rather, it's an example of array structures. Okay, so that's what we'll do today. And then the next lecture is the last one. We'll explore some applications of topological recursion. So I'm not sure exactly which ones, but probably we'll talk about enumerative geometry. So how you can get Hurwitz numbers, Gromov-Norton invariants, topological strings, all of that from topological recursion. And we might talk about quantum curves and WKB analysis in the context of topological recursion. So I'll be for next lecture. Okay, so let's get started. So what have we seen so far? So we basically saw 2 different structures, right? The first lecture was about the first 1.5 lecture was about array structures. And what was that? Just to remind you, so we basically were characterizing left ideals. So I was a left ideal and the Riesz-Waal algebra. And we characterize what properties this ideal has to satisfy so that there's always a unique solution to the constraints, or basically a unique partition function that is annihilated by this ideal. Okay, so the conditions are that this left ideal generated by a set of differential operator, collection of differential operator HA, such that 2 conditions are satisfied. First is that the operator starts with the derivative, and there is one such operator for each variable in your variable set. And the second condition was the ideal condition, which is that the commutator of the ideal with itself is within h bar square times the ideal. That was the definition of array ideals or array structures. And the main theorem in this context is that there always exists a partition function. So this is an object z, which is exponential of a series in the variables, such that, well, the annihilator of this partition function in the Riesz-Waal algebra is the ideal you start with. So equivalently, well, not equivalently, but it implies that the annihilator kills z, right? So that implies this. So the HA kills z, and that gives recursion relations for the coefficients in the partition functions, which we called FGS, with some indices. Okay, so this was the first lecture and a half. Okay, so this is a very clean, simple construction, and that gives a set of recursion relations. And we saw some interesting examples: Kontsevich-Witten, BGW, Mirzakhani, and so on and so forth. Okay, the other construction that we studied was the rest of the lectures so far was about topological recursion. So what was this? This was in other formulation, recursive formulation, that looks completely different a priori. So the initial data here is quite different. We're not talking about differential operators whatsoever. Instead, we start with the data of a spectral curve. And what is this? This was a quadruple. So I'm not going to restate the definition here, but we had these 4 objects here, and together they form the geometry of a spectral curve. Now, we studied a magical formula called topological recursion, which involves basically residue analysis at the ramification points of the branch covering X, right? And this is the construction, and the output of this beautiful recursive formula is what I call a system of correlators. So this is a collection of object omega GNs that are symmetric differentials living on the spectral curve. And the key here is that it satisfies the projection property, so you can expand in the basis naturally defined at the ramification point. So there's one such basis for each ramification point. And through this expansion, we ended up with coefficients of the expansions of the correlators that are also called FGNs. So I had multi-indices here. Let me forget about the multi-indices. just for simplicity. So in other words, let's just think of having a single identification point if you want. Otherwise, you get multi-indices. All right, so these are the two things we've seen so far. And obviously, they look very different. The constructions are very different, but the end result is very similar. As we've seen, the recursive structures we end up with are very similar. So certainly that can't be a coincidence, right? As mathematicians or physicists, we're like conspiracists, right? We see things that look the same, then it can't be a coincidence. So we have to find a reason. Of course, we're not conspiracists because we're actually going to prove the result. And if it is a coincidence, then it is a coincidence. But the fact is that it's not a coincidence here. So there is a connection between these two constructions, and this is what we'll explore today. Okay, so what is the connection? Great. So the connection is the so-called loop equations. Okay, so what are loop equations? So let me first give you a bit of context. So loop equations come from matrix models. So if you don't know about matrix models, that's fine. We're not going to say much here about matrix models, but there's a fascinating subject. So there's some great lecture notes online that you can find. There are many sets of lecture notes on matrix models. Marcos Marinho has some. Bertrand Henao has some. So you can read about matrix models. What we're focusing here is mostly on Hermitian matrix models. So what we're doing is basically, in mathematics, it's also called random matrix integrals. So we're integrating over the space of Hermitian matrices. That's an example of a quantum field theory if you want, but where there's no space-time. So space-time is like point, there's no dimension, but your fields are actually matrices. So there's some sort of gauge invariance here. Okay, so in the context of matrix models, these equations, the loop equations, have different names sometimes. So you may see them called Schwinger-Dyson equations or Dyson-Schwinger, depending on the person writing the paper. They're also called wide identities because they are the wide identities as in quantum field theories. Probably there are different names too. But the main names are these, and loop equations is what I'm going to use here. Okay, and the origin of the loop equations, as I said, is in the context of matrix models. So there are many ways you can derive them in matrix models, but let me just give you a little bit the context. So the objects that you're interested in matrix models would be called omega, not omega, Wn usually. So these are also called resolvents in matrix models. And what they are is basically generating series for some of the interesting observables in matrix models, which are the expectation values of product of traces and matrices. So let me just write down the definition of these objects. So you would be summing over things that look like this with some x variables here. Now, usually in matrix models, these are just series, but we will upgrade them to differentials, symmetric differentials, because that's what we want to get topological recursion. So, and these are very natural objects because you see, so expectation values here just means you insert that into your path integral, which in this case is an integral over the space of matrices. M is a Hermitian matrix, certain dimension n. So you integrate over the space of n by n Hermitian matrices. And these are the type of observables. So you want observables that are invariant under basically diagonalization of your matrices. So traces, product of traces are such things. So these are very natural observables. And this is a natural object to consider in matrix models. Great. Now, one very nice thing with matrix models is you can do a large n expansions. N is the dimension of your matrices that you integrate over. Okay. So if you do that very generally, this is sometimes called topological type. So it's not always true that there is such a large n expansions, but when there is, it's called a topological type. This expansion is basically saying that you can expand these resolvent here as series in 1 over n. Okay, so that looks like this. And that defines some objects WGN. Okay, so this is one kind of particular asymptotic limit you can do to study matrix models. And it turns out to be interesting for many different reasons in the context of matrix models. And the key statement for us is that these WGN satisfy a set of equations, which are called loop equations. And this is something you can show in terms of matrix models in various ways. So these are actually fairly easy to get in matrix models. You can get them, for example, there are many ways to do it. You can show that these equations are satisfied by just simply looking at reparameterization invariance of your integrals. So basically, just reparameterizing the space of matrices shouldn't change the value of the integral, just like U substitution for definite integrals if you want. So that's one way you can get that. You could, there's a very direct way of getting those, which is by integrating total derivatives in your matrix integrals. So of course, I don't have time to explain any of that, but the point is that these have been derived, and they're Ward identities, Schwinger-Dyson equations, they've been derived in many different ways. Okay, but this is a set of equations that these WGNs satisfy. And then the key statement is that they can be solved recursively. And recursively here is over the power of 1 over n. So this is over 2g minus 2 plus. Okay, and this is basically what was done in the original paper of Latam, and that's what gives rise to topological recursion. Okay, so that's the context of matrix model. Now I should say here we're doing what's called beta equals to 1, which is the Hermitian case. Beta here is the power, or rather 2 times beta is the power of the Van der Waals determinant that appears when you write the matrix integrals over eigenvalues. Now, you can do it for other choices of beta to get, for example, unitary matrices, real matrices, and then you'll get different looking loop equations and solutions. And these are interesting, and they give rise to beta deformed topological recursion and so on, but we won't have time to talk about this here. So are there heuristic reasons why there should be factors of x to the k plus 1 in the resolvent? Well, I mean, the idea here is just you're constructing a generating series for expectation values of traces of matrices. So, you know, traces of products of matrices are indexed by the exponents, right? K1 to Kn. So you just introduce variable x1 to xn so that you get a generating series. Now, why is it 1 over x instead of x? I'm not sure that there is much. It's just a generating series, right? Yeah, I don't think that. Yeah, I mean, for us, it will play an important role because these WNs become actually globally defined differentials, and this is an expansion at infinity or a pole on the spectral curve. But yeah, here's just a generating series. What is the bracket? So the bracket here, so this bracket, I think is what you mean. This means expectation value, just as is standard in physics. So what this means here, it means that you have a matrix model. So a matrix model is going to be some integral over the space of matrices of the exponential of some potential here. Well, there's a trace here. Roughly speaking, it's something like this, right? Integrated over matrices, and expectation values just mean you insert this here inside your integral, just as is standard in quantum field theory. Right, this is your path integral, which is now an integral over the space of matrices. Okay. In any case, these are not lectures on matrix models, so I won't have time to explain more. But if as I said, if you're interested, there's also a beautiful book by Bertrand Hénard that talks about matrix models in lots of different ways. And there's been a lot of work on matrix models, so there are many good resources out there. Okay, but the cool thing is that they satisfy equations. And for us, what is important is that the system of equation I just talked about, which is called loop equations in the context of matrix models, can be formulated abstractly. So what does it mean? So what it means is that it can be formulated without reference to a matrix model. And you can study these equations for what they are. That's exactly the idea of topological recursion, right? Remember, I told you the motivation of the original paper was basically, here's a formula, what is it calculating? Well, this formula, as we'll see, it provides a solution of these loop equations. So we can do the same thing. We can talk about this system of equations as an abstract system of equations and study the properties. And that's exactly how we will connect topological recursion with area structures. So sometimes these, in this context, these are called abstract loop equations, just to make it clear that we are not talking about the resolvents of a matrix model necessarily, but for us, we're just going to call them loop equations because I don't want to write abstract everywhere. Okay, but it's basically the system of equations formulated without reference to an underlying matrix models. Okay, so what is this system of equations? Okay, so let me define the loop equations, and again, I'll define it abstractly as I said, but this is exactly the set of equations that is satisfied by the resolvent or the 1 over n expansion of the resolvents of the matrix. Okay, so my assumption here is going to be the ones that I've been making so far in these lectures, which is that all ramification points are simple. This is just to simplify the exposition for these lectures, but you can generalize all of that to r greater than 2, and I'll mention how this goes. Okay, so what are the loop equations? So here's the definition. So here we are being abstract, as I said. So we just start with a system of correlators on a spectral curve. In the context of matrix models, these would be the 1 over n expansion of the resolvent, but now thought of as differential forms living on a spectral curve, not just generating series for expectation values of traces, matrices. Okay, and then we say, so there's going to be 2 loop equations in these notes. So we say that it satisfies what's called the linear loop equation. If the following condition is satisfied, you write it 1 for the linear loop equation. So what you do is the following. So let me write it down. You take a correlator. So this, okay, I forgot to write this, but if this is satisfied, not the right pen. So this is for all 2g minus 2 plus n greater than 0. So all stable correlators. So what you do is you take a correlator. The first variable is distinguished. You sum, same correlator, but with sigma of u as the first variable. Remember, sigma is this local involution near a ramification point. So this is only locally defined near a ramification point. And the condition is that this object that I just wrote is holomorphic at u equals a. And this is for all ramification points. Okay, so there's one such equation for each ramification point, in other words. And what you're doing here is you're just adding the omega gn with itself, but with the first variable being u or sigma of u. Okay. Now, if the involution is globally defined by and it's just changing the sign, which was the example in the area case and so on that we've seen, what this gives is just some sort of evenness property or odd property for the, or rather that the omega gns are odd, so the coefficients of the differentials are actually even. So that's related to when I was saying the FGNs are only non-zero if all the entries in the FGNs are odd. This is where it comes from, as we'll see. Okay, and here I'm dividing by dx. So this again is just a shorthand notation for saying, well, the omega gns are differentials in u, dividing by dx of u. So that is just a function of u. Just cancel the d's. Yeah. Okay, so that's a loop equation. This is locally defined. That's a local condition at the ramification point. The quadratic loop equation is the following. So we say that it satisfies the quadratic loop equation if, again, for 2g minus 2 plus n greater than 0. I don't know if you can read. And now the condition is similar but slightly more complicated. So now I'm dividing by the xu square, and then I'll have the following expression, which, you know, will remind you of something. First term, second term here is a sum. It's like this. And omega g2, j plus 1, sigma of u, j. Okay, so this is the expression. Again, this is locally defined at the ramification point. And the condition is now two parts. So it's either holomorphic. Condition is that it's either holomorphic at u equals to a if a is a ramification point of Airy type, right? You remember what that means. And if it's Bessel type, then it has at most a double. Okay, so this is what's called loop equations. So I guess I could put an S here. Because there's one equation, one such equation for all g and n, such that 2g minus 2 plus n is greater than 0. Now, these look like they're coming out of nowhere, but again, these are exactly the Schwinger-Dyson equations that you get from matrix models. Or at least it's an abstract reformulation of the Schwinger-Dyson equations. What you would get in matrix models is actually more explicit in some way, because you would get an equality between these objects here and something else that is constructed out of the data of the matrix model. But that something else is very complicated. And in fact, it doesn't matter what it is. All that matters is its pole structure. So in the end, all that you care about to solve the loop equations is exactly the abstract statement here. Okay, so this is in other words, we've extracted the information that comes out of the Schwinger-Dyson equations. Okay, and there's a few things I need to write down here just to be clear. One thing here is that there's no prime on the sum. So this is the sum here. Now, remember when we did topological recursion, we had a prime here, which meant that omega 0, 1 are not included. Now, here they must be included. That is very important. So the terms with omega 0, 1 are included here. So this is not really a recursive statement, like in the sense that, well, it's not an equality in any case. It's just a constraint on these conditions. But the point here is that omega 0, 1 appears, so omega GNs will appear here as well. Okay, so that's one remark. And the other remark here is that if you look at the case r greater than 2, which I will not do, you will have more equations. So that we only have linear and quadratic because we stop at r equals to 2. But if you had r equals 3, say you would get linear loop equations, quadratic loop equations, and cubic loop equations, which would look similar, but like one level deeper, let's say in the recursive structure here. In general, you're going to get basically r different loop equations, linear, quadratic, cubic, and so on. And one thing to note as well is that the pole condition, so the constraint which forms the loop equation, depends on the local behavior. So it depends on this parameter S that I introduced. So this is why for the quadratic, we had to distinguish between Airy type and Bessel type. So in general, you have you can write it down. This is written in many papers. You can write down the general formula for the loop equations. And it's the statement that these kind of combinations have a pole of order at most, blah, blah, which depends on R and S. Okay, great. So these are the loop equations. Now, this is fairly abstract, as I said. They're called abstract loop equations. Any questions on those? Okay, so how is that connected to TR and Airy structures? So the main question here, of course, is can we solve loop equations, right? This is the question. more precisely, one could ask, what is the set or space of solutions of loop equations? So by loop equations, I always mean both simultaneously, the linear and quadratic equations. And this is also relevant in matrix models. As we'll see, there is one solution in matrix model, which is the normalized one, which is the one that we'll focus on. But other solutions appear in different contexts in matrix models as well. So it's a good question to ask, what is the space of solutions in general? And from this abstract point of view, this was mostly studied in, or at least it was mostly studied in a paper of Boho and Chadrin, 2015, I think, called Blob Topological Recursion, Properties and Applications. So it's a great paper. And the result here is actually quite nice. So let me state the result, because that will be important. So I have to recall this projection that we introduced before. So remember, in the data of a spectral curve, there's an omega 02, which plays a very important role. And out of omega 02, we can define a projection operator B hat at any point P. What it does is it takes a one form and constructs, or at least takes the local data of a one form at the point P and constructs a globally defined one form, which has the same principal part at the point P. So what it means is that for any meromorphic one form, lambda, we can always decompose it in the following way. So we can write lambda as being, so we're going to distinguish again the ramification point. These are the important points. So we can always project the one form at each of these points, right? So these constructs, this is basically a one form that is the sum of the principal parts of the original lambda, but this is not usually equal to lambda. So there's going to be an extra term here, which I'm going to write h of lambda, and that extra term is going to be a holomorphic one form, right? So this would be holomorphic on the Riemann surface. Okay, so that's for any meromorphic, sorry, that would be for any meromorphic one form that only has poles at the ramification points, right? So if the meromorphic one forms only has poles at the ramification points, you can project at each of these points. You're constructing a new one form that has the same principal parts, but the way you project depends on omega 02, and that means that here you will get an extra term here, which would be holomorphic at the ramification point. Okay, and if lambda satisfies the projection property, this extra term is 0, right? So that would be a statement here. So note the projection property on this set of ramification points. This is something we talked about. Is the statement that this extra term is 0. Right, so it's just equal to its projection, the sum of its projection at the ramification points. Okay, so you can always do that for any meromorphic one form that only has poles at the ramification points. So I should add that. That only has poles on. Okay, so we're going to define here what we call the blobs. Okay, so let omega gn be a system of correlators. Now, I'm not going to assume anything more than the fact that it's a system of correlators. So in other words, we know that the omega gns have only poles at the ramification points for 2g minus 2 plus n greater than 0. So we're going to call the blobs. This name was introduced in that paper of Boho and Chadrin as being the purely holomorphic part of those, using the projection B hat that is defined by the spectral curve. So in other words, let's call them phi gn. These would be you project in each variables, and then you keep the holomorphic part. This is purely holomorphic in all variables. Okay, and then the projection property, so I could write it here, but it's the statement I just wrote. Projection property is the statement that blobs vanish. If the omega gn satisfy the projection property, then the blobs are zero. Okay, but in general, for a system of correlators, there's no reason why it should be zero. In other words, there's no reason why omega gn should be the sum of its principal parts at the ramification points using the projection that we just talked about. Okay, any questions on this? I know it's quite abstract. Okay, but this is the main theorem. So this is what you need to understand the space of solutions of loop equations. So the main theorem, this is again Bourreau and Chadwin. Great paper, should have a look. The main theorem here is that if you pick any set of symmetric differentials, so let's pick a collection of symmetric, holomorphic, symmetric M differentials on your spectral curve. Then there is a unique, there always exists a unique solution or system of correlators with a GN on the spectral curve, of course, that satisfies the loop equation. So linear and quadratic equations, and such that the blobs of that system are equal to the phi GN you just specified. So in other words, reject, or rather keep the holomorphic part in all variables, you'll get the blobs. And that's fantastic. Okay, and this basically is the space of solutions. And not only is that true, it's like a one-to-one correspondence, so every solution is going to be a dot form. Okay, so every solution, assuming that omega GNs only have poles and ramification points, will be of that. Great, so that is the answer to the question, what is the space of solutions of loop equations? It's this. What it says here is basically you should think of these blobs or these phi GNs here as initial data, right? If you're interested in solving the loop equations, what you want to do is specify this infinite collection of holomorphic symmetric differentials, and then you can solve the loop equations. And we'll see how we can actually solve it. What happens is you get some sort of recursion, which in this case, very generally, is not really a recursion. Well, it is a recursion, but there's an infinite set of data. Yeah, so it's kind of it's not that useful, right? For every G and N, you have a new phi that you need to specify. Okay, but this would be the equation satisfied the omega GN here has become known as blobbed topological recursion since the paper Bourreau and Chadwin. And it has found various applications. But the main interest is in the solution where the blobs vanish, right? And it follows, this is a corollary from the previous theorem, is that there is a unique, the first part of this new theorem is a corollary, which is that there's a unique solution to the loop equations that satisfies the projection property. Oops. So why is that a corollary? Well, this is just a choice of blobs, right? The projection property is just the choice where you take all the blobs to be zero, perfectly valid choice, simplest possible choice. So by the previous theorem, then there's a unique solution. Why I didn't call that a corollary is that second part needs to be proven, which is that this solution satisfies topological recursion. Okay, so that is the origin of topological recursion. That's where it comes from. It's basically solving the loop equations, but it's singling out a particular solution, which is the one that has no blobs, that satisfies the projection property, normalized on A cycles, all the same depending on your point of view. Okay, this is a very important theorem, so it was proven in many places in a kind of higher and higher level of complexity, if you want. So I'm going to write a few references here, but there are many places. So first there was, of course, proved in Latam. Then, of course, the paper above, Shadrin, is where they talked about the blood topological recursion statement. But the projection property, the second statement here, is also proved in the appendix of a paper of mine with Boho and Chidambaran, Krzyk, and Lushenko. Also, Boho, Kramer, and Schuler afterwards provided a more extensive proof. And perhaps the more complete, the most complete proof might be in the recent paper I wrote with Boho and Chidambaran, Kramer, and Shadrin, where we study limits in topological recursion. Maybe this is the most complete in the sense that we look at the very, very general case. Now, in the papers I'm referring to after Boho-Shadrin here, what's studied is the general statement. So for general R, not just pi equals 2, where the combinatorics are quite a bit more involved, but the statement is the same. There's a unique solution to the loop equations. Now there's R loop equations that satisfies the projection property and is given by the generalization of topological recursion. Okay, so if you're interested in this statement, I would humbly suggest maybe the last reference here is the most complete proof, but it has been proven in a lot of different papers. So there's lots of resources on this. Okay, and I just want to tell you a little bit how this proof goes because it's actually quite interesting. But of course, we can't go through all the details because it's not obvious. I mean, what is obvious, of course, is the statement that there's a unique solution satisfy the projection property, assuming the theorem above. I mean, it's a consequence of it. But the second statement is that it satisfies topological recursions. How do you get that? So how do you get, if you start from these equations, these two constraints on these particular objects, how do you show that if you impose the projection property, then the solution is given by topological recursion? Right? This is basically formal manipulations of the equations, but they're quite non-trivial if you've never done it before. So I would do it in 3 steps, and I just want to highlight the steps, and then you can go on and look at the papers and the details. Or you can try to do it yourself. Very, very good exercise. So the first step is to multiply, and again, there are different ways of doing it, but this is, I think, the most direct way. So the first step is to multiply the quadratic loop equation. This is the interesting one in many ways. This is where the recursive structure of topological recursion appears. So you multiply the quadratic loop equations by this particular object. Why you want to do that is basically because this is what's going to work. But so you know it. You've played with these equations quite a bit. But you multiply by this, and then, I mean, as you can see, this, if you remember topological recursion, well, the dxu square here is just to cancel the dxu square in the denominator, and this is exactly what appears in the recursion kernel. So that's kind of what you want to get. And what you want to show is that this is a holomorphic one form in U at the ramification point. Okay, this is just pole counting. So this is a straightforward step because you just take the constraint of the quadratic loop equations, multiply, look at what happens to poles at U going to A, and then you get that. It's a holomorphic one. Okay. And you also see why we had different constraints. So for area and Bessel type, because omega 0,1 behaves differently here in the area and Bessel type. So the constraints are exactly such that this new one form you constructed is always holomorphic. Okay, but what does it mean to be holomorphic? It means that if you use our favorite projection and you project the xu square over what I just introduced, and then put the quadratic loop equation here, you're going to get 0. Oop. Sorry. Looks like it stopped. Still there. Ah, just give me a second. I'll reload. Okay, still here. Took a while. Can you see what I wrote? Yes. It's kind of slow. I'm not sure what's going on. Okay, let me maybe try to reload. Okay. So the statement as a holomorphic one form is the same statement or as saying that if you project, in fact, this is a consequence, it would be a statement for each of those that it's equal to 0. The principal parts at the ramification points are 0, but this is what it says it says as holomorphic at the ramification point. So that's exactly what this is saying. Right? So the principal parts are 0. That's what you. Okay, so that's the first step. Then the second step, okay, this is really, I don't know what's going on. So let me just give me a second. I'll try to restart this. I think the connection is not very good. Which is unfortunate. Okay, let's try. All right, so what you do next is that you rearrange terms. Nah. Well, we're gonna keep going, but it's kind of slow. I'm sorry. So you can hear me fine, right? The voice is fine.
Yes, if you want, we can go to a break and then you can check.
Yeah, I just don't know what's going on. But let's just finish this. I think that should work. And then we can take a break and I'll look.
Okay.
Let's just finish the proof here. So yeah, we can rearrange terms in the quadratic loop equations. That's the second step. And this is where you use the linear loop equations. Okay, and what you'll get is, okay, this is not working. I'm writing beautiful stuff. None of it appears. Okay. So you rearrange the term in the quadratic equations to show that you can maybe we will have to take a break. I'm not sure what's going on. Is that okay? So let me just finish this sketch of the proof that was interrupted. There was a question that's also in the chat, so I will actually it's a complicated question, so maybe I keep it for later because I'm not sure how to answer it. But let me finish this proof. So just to remind you what we're doing here, so we're trying to show that topological recursion reconstructs the unique solution of the loop equations that satisfy the projection property. So the first step was to just multiply by this thing that appears in the recursion kernel and show that it's a holomorphic one. So in other words, the sum of the projection at the ramification points is 0. And then the second step here is just manipulations of equations. So this is where you have to do some work. But using the linear loop equations, you can rearrange the terms in the loop equations inside this projection operators and show that you can rewrite it as the first term here, which remember this is the omega hat that I introduced, omega bar, sorry, that I introduced earlier, which was basically this thing that appears on the right-hand side of topological recursion. And this is the omega GN. So what you're doing here, so in omega bar, there's no omega 01. So what you're kind of doing here is singling out or extracting the contributions from omega 01 in the quadratic loop equations. And then you show that they basically cancel with the denominator and you can isolate omega GN. So this is kind of probably a little confusing here. How do you do that? And really you have to do it. The only way to understand how this works is to do the calculation. But this is the reason why we divide by this. It's precisely such that we can isolate omega GNs here inside the loop equations. And that allows us to bring it on the left-hand side, right? So if you just rewrite this as an equality, so let's bring the second term on the left-hand side. So you get this statement here. So the projection is always in the first variable, right? That's why I put a dot. And on the right-hand side, you have the right-hand side of topological recursion, which was the projection of this locally defined object, omega bar GN, at the point A. Okay, so that is there's a statement here. Now, that is not the end of the story. The last step, however, is straightforward. It's to impose that they satisfy the projection property. So if the system of correlators satisfies the projection property, then you get topological recursion because the left-hand side is equal to omega GN. Okay, I should have some Z1s here on the, the projection operator, replace the variable by Z1. So my notation might, this is some Z1 missing here everywhere. But essentially that's what it is. So the left-hand side here is because if it satisfies the projection property, the omega GNs are just equal to the sum of its projections or its principal parts. So this is omega GN. So what you've done is completely solve recursively and you get topological recursion. Okay, so that is basically the way you prove that. Now, what you see here is that if you don't impose the projection property, then the left-hand side here is not the omega GN, right? So you will not actually get topological recursion. What you'll get is some recursive formula, but what it fixes is only the principal parts of the omega GN. So that will not reconstruct the full omega GN recursively. Okay, so that is that's basically how you get topological recursion from the loop equations. Okay, makes sense. So that's beautiful. Now, of course, as I said, it's the devil is in the details. So if you do these steps, it's not so obvious. But if you do it just for the R equals 2 case, you can actually do it very explicitly. So it's not too bad. If you do the general R case, then the combinatorics get fairly complex, as always, in this field. So it obscures what you're actually doing. But the essence is exactly this. Okay, so the moral here is that you get TR, you get a fully recursive structures only if you impose projection property. If you look at the other solutions of the loop equations, the blob solution, you basically, the recursive structure here fixes the principal parts, but you have a holomorphic data that you need to add for every GNN, so it's not fully recursive. It's part of the initial data. One thing I want to mention as well, that's just a remark. But I mentioned before that there are a few variations of topological recursion. So one of them is called log-TR, which is from very recently, from 2 years ago, ABDKS. I forget all the authors here, Alexandrov, Birshkov, Dunin-Barkovsky, Kazarian, I think, and Chagrin. And hopefully I have the right ones. They have a series of papers where they explore log-TR and generalized TR, as I mentioned before, which are based on symplectic invariance. And in the case of log-TR, what it does is basically it proposes another way of singling out a solution of the loop equation. So it's an alternative condition. This is not the projection property, it's slightly different. Alternative condition for solving loop equations, and so alternative to the projection property. And basically the reason here is that they want to preserve symplectic invariance, which I've mentioned before for the free energies. And for most spectral curves, for maybe not most, for a large class of spectral curves, their alternative condition is actually the same as the projection property, but in some cases it is different, and it restores symplectic invariance for these cases where it was not satisfied. So it's basically singling out a different solution of the loop equation. So it's not like a fully blob solution in the sense that the blobs are not arbitrary. Here they're fixed in a very nice way, and that's what defines this log TR, if in my understanding. Okay, that's just a remark. If you look at these papers, why basically what they end up with is a topological recursion formula, but there's some extra terms there, and that's where it comes from. Okay, so this is the first part of what we want to do today. So that's where we would have taken a break if my internet was working well. So now we're going to do the second part, which is to connect loop equations to the other direction, which is area structures. So for the question in the chat, if that's okay, maybe we can talk about it at the end, because I'm not exactly sure what to say about it. So, but thank you for the question. I encourage you to ask more questions. That's great. It's very hard to make it interactive in these virtual lectures. So, yeah. Okay, so loop equations as differential constraints. So what we've done so far is we've shown that loop equations plus projection property gives rise to topological recursion. To be more precise, what we've shown is that if there exists a solution to the loop equation satisfying the projection property, it is given by topological recursion. And then in the case of R equals 2, then we know that there always exists a solution because we know that topological recursion always produces symmetry correlators. But in general, as we'll see, this is not obvious. Okay, but this is what we know here. That's the first connection. And the second connection would be, can we start with loop equations plus projection property and get an area structure? And if so, what kind? What would that look like? What kind of area structures are we going to get if we do it this way? And in some ways, this is more direct. So because to solve loop equations as topological recursion, I showed you how to do it. You do have to manipulate the equations quite a bit, especially if you do the channel R. It's kind of some sort of manipulations, but it's not clear why you would have done that if you don't already know the answer in the first place. Well, this is in a way more direct. So the idea here is quite simple, is to recast the loop equations as differential constraints on a partition function. So first I need to tell you how we're going to construct the partition function, and then we will show that we can rewrite the loop equations as the action of differential operators on that partition function. Okay, so that's the second direction that will provide a connection between topological recursion and area structures. Okay, so we'll do that again in a few steps. So I'll tell you how we do it because the construction is also quite nice here. So we start with a system of correlators, as always, that satisfies the loop equations. Well, let's just start, generally speaking, with just a system of correlators on the spectral curve. So again, I'm doing the same assumptions as usual, just for simplicity for these lectures. I'm going to do a further assumption here. So first, I still assume that it's only a simple ramification, R equals 2. But I'm going to do a further assumption is that there is a single ramification point. So in other words, the ramification set here is only one point, wherever it is. This is not needed whatsoever. Everything goes through with many ramification points, but we have to deal with multi-indices. So it's just a pain to write down. So for clarity, I won't do it here. Okay, but the first step here is simple. So we're kind of proceeding in the reverse direction. So when we shown that topological recursion provides a solution of the loop equation, the projection property was kind of imposed at the end. So now we're going to start by imposing the projection property. So we're going to impose first that the omega GNs satisfy the projection property. And why is because we need that to define the partition function in the first place. So why? Well, if it satisfies the projection property, you can expand index C basis. Right? So you can write down, so here there's a single ramification point, so there's a single C basis. So I sum over all X's, negative X's. Okay, and that defines a set of coefficients. FGNs only finitely many are non-zero. Yeah. Okay, that's only true if it satisfies the projection property, because otherwise you would get X's with positive K's and you can get infinite number of them. And that's, yeah, that would be different. Okay, but if it does satisfy the projection property, we can do that. And then we can construct a partition function. Okay, so we construct the partition function as usual, take the exponential of the sum here. So as always, G is an N and N is an N star. And I have my coefficients. So one way to think about it is that we are just indexing, we're just constructing different generating series for these coefficients FGN. The first we get these FGNs as coefficients of the omega GNs. Second, we construct them as coefficients of a partition function. Okay, so it's just different way of encoding the same information if you want. Okay, so that's the first step. Now that's cool. Now this is for all the stable ones, so 2G minus 2 plus N greater than 0. For the unstable ones, omega 0,1 and omega 0,2, you can also write them in terms of the Xi basis. So you need that to be able to proceed. So here you can define the F01, but now there will be positive X's. So I did not define these positive X's before, but the way they're defined is they're just defined locally near the ramification point, just as powers of the local coordinate. So that's only defined locally. So the Xi with negative Xi minus K are defined globally. Xi K are just defined locally, but they are holomorphic. So these are objects that have zeros at the point, at the ramification point of higher and higher degree. Okay, because omega 0,1 is holomorphic at the ramification point. So that's why you need to expand, but now you're expanding in terms of positive X's. And omega 0,2, you can generally replace, I mean, you have to be quite careful with the omega 0,2. So I'm not going to be very careful here. You'll have to be a little more careful than that. But the main thing that you need is that you can replace it by something like this. So this is for an expansion where Z1 goes to A and Z2 is away from the ramification point. Okay, so, and you can see that just do an expansion of 1 over Z1 minus Z2 square, where Z1 goes to point A and Z2 is away. This is holomorphic at Z1 going to A, right? If Z2 is away from A, so this is a holomorphic thing. So you're basically expanding in powers Z1, and then it comes with basically 1 over Z2 squared plus Z1 over Z2 cubed plus so on, with the coefficient is K. That's basically what you get from this expansion, but here in general, omega 0,2 is not necessarily just this, so that's why you have to use the Xi basis, but that's really just, in a sense, what it is. Okay, that's what's mostly relevant, but you have to be quite careful with omega 0,2. I'm not being precise. You have to treat it a little more carefully than that. Essentially, you can replace all the omega GNs by expressions in terms of X's, right? And these defines the coefficients of GNs and F01, and here the expansion of omega 0,2. Okay, so this is the first step that gives you the partition function. And now the second step, which is the key step, is to reformulate the loop equations Actually, that's not the key step. The third one is the key step. So the second one is pretty straightforward. So you want to reformulate them as residues. So this is straightforward. So the linear loop equation was the statement that this expression, so forget about the res for a second. So this expression here was holomorphic at the ramification point. So what does it mean to be holomorphic at the ramification point? It means that if I multiply by c, k, u for any k, and I take the residue, I'll get 0. This is for all positive k. Right? So you just basically multiply by powers of u, or the local variable here, and the statement that this is homomorphic is the same statement that you will never get the residue will always be 0. Yes. Okay, and then the quadratic equation is the same thing, but now you're going to multiply the quadratic loop equation. So you take the exact same statement, you multiply by ck u, but now you have dxu square, and maybe I won't rewrite everything here, but this is the quadratic loop equation, or rather the quadratic stuff here. And the statement is that this is equal to 0, but now this is true for all k greater or equal to 1 if A is arytide, right? Because the statement was that this object was holomorphic, but for Bessel type, it was that it's can have a pole of order at most 2. So it means that these are 0 only for k greater or equal to 3. Okay, but that's just basically a direct translation of the loop equation. That would be another way of formulating loop equations. But the key step is step 3, which is, or at least, well, I guess step 4 is the key step. Step 3 is important too. So now we're going to substitute the expansion that we just used in the x's, right? So you just have these x's, and you substitute it in the residue formula that I just wrote above, and that will give recursion relations for the coefficients. Okay, so that might not be clear, but if you do it, that's basically what you end up with. Or in fact, it's not really necessarily recursion relations if you want, because you still, it's just an equality of something equals to 0, but you can solve recursively. You can isolate or extract FGNs on one side. And the point here is that this is some algebraic equations you get, but the coefficients of these recursion relations are going to be given by simple expressions that involve taking the residue of products of x's. So schematically would look like this, right? So you just basically expand in x's everywhere, and then you just rewrite that as a recursion for the coefficients. These are just numbers. And then the coefficients of these recursions are going to be given by these residues of x's, which in principle you can evaluate. If you're given a spectral curve, you know the x's, you can evaluate all these coefficients very explicitly. So that gives you an explicit recursive formula. And the last step, when you have that, is to now rewrite that as differential constraints. So what you do last is you construct differential operators, HA, such that when you act on Z, this gives you the same recursion. Okay, so I'll do some examples, so it will be clearer, hopefully. But this is how you do it, essentially. So this was carried in some detail in this paper I've mentioned a number of times, myself with Gaetan Borot, Krzyk, Chelambaram, and Noshenko, but we do it for the general R there. So if you look at that, it might be like heavy in terms of notation, but essentially that's exactly what we're doing there. But if you do it for the R equals 2 case, what you will end up, if you do that, is that the differential operators you get are going to be quadratic differential operators. And it's not too hard to see why, because the structure of the quadratic loop equations is exactly what you get when you act with two derivatives on an exponential, as we've seen when we talked about area structures. So you get precisely these kind of expressions that I had very early on. Something like this, where all of these coefficients here, the A, B, C, D tensors here, are given by explicit formula involving residues of products of C's. So basically, all the data of the spectral curve is encoded in these tensors. Okay, so that's pretty cool. This was also done in some detail for the quadratic case. Well, first by Concevich-Subelman, but also in this ABCD of topological recursion paper by Anderson, Boho, Chekhov, and Ahante. Okay, so this is all very nice. All this is again, just rephrasing. So you're just starting with the loop equations and basically recasting them as the action of differential operators on the partition function. But that doesn't tell you whether it's an area structure. The question here is, okay, you construct a left ideal, right, generated by these operators. The question is, does this ideal satisfy this condition? This is the key condition. I mean, the operators have the right form. That's clear. That follows directly from the form of the loop equations if you do the calculation. But do they satisfy this condition? That's a very non-trivial question. So in the case of R equals 2 in ABCD of topological recursion paper, they actually show that explicitly in the Concevich-Subelman paper as well. And it ends up, if you do that very, very calculationally, very computationally, you end up with some relations between ABCD that have to be satisfied, some complicated quadratic relations between those, and you can show that they are satisfied, and that's the way you can prove that. But it's very non-trivial, right? So you would want to have a more systematic way of showing that. Fortunately, there is, so it's kind of nice. And that's where we'll do some examples because that will explain what is going on. So what do these HA really look like? Okay, so any question on this? This is like, I know this is a lot of steps and a lot of formal manipulations, but I think it's good to explain them because these papers, there's a lot of papers on these things and they're quite obscure, I think, to the non-experts, just because the notation is very complicated. But often the logic behind is not that complicated. Okay, so let me just show you what happens. So if you can do exactly what I just said, start with the loop equations on the area spectral curve. Good. Start with the loop equations on the area spectral curve, and then just sorry, I lost the chat. Right. Start with the loop equation of the area spectral curve. Do the 4 steps I just said. Construct the differential operators. What are you going to get? Okay, what you're going to get is the following. So let me introduce first 2 operators. I'm going to call the first one W1K, and then the second one W2K. So what are those? So these are operators in the Riesval algebra. So the J's were introduced a while back. Positive ones are derivatives. 0, 1, we're going to set to 0, although it doesn't have to be, but let's set it to 0 for now. And the negative ones are just variables we scale by n. So that's a representation of a Heisenberg algebra. Okay, so I introduced these operators. These are not random. These are the modes. If you know about conformal field theory or vertex operator algebras, VOAs, these are the modes of some fields that strongly generate an algebra called W of GL2 at central charge 1, or what's called self-dual level. This is, of course, a representation or a module, if you want, for this VOA. And the way it's constructed is not that simple. So what you do is that you start with a Z2 twisted module or representation for the Heisenberg algebra of two free bosons. So WGL2 is a W algebra, obviously, and you can construct it as a subalgebra of the Heisenberg algebra of two free bosons. Now you could there are many you can just construct it directly as an embedding. It's in terms of elementary symmetric polynomials of the free bosons, but then you can do you construct a twisted representation for this Heisenberg algebra where you exchange the two bosons and then you restrict to the W algebra and you get precisely this expression here. Okay, so this had been studied quite a bit. In the literature, the twist here is important. It basically is a VOA explanation of this involution that we have in topological recursion that exchanges the two sheets at the ramification point. But that's at a higher abstraction level than what I'm doing here. Okay, anyway, so these are the operators you want, but that's not quite what you're going to get. So the differential constraints that you will get if you do the 4 steps that I said is going to be almost those. The only difference is you conjugate by this particular exponential. G3 is the third mode, so it's basically del 3 derivative with respect to the third variable. Okay, so the conjugation here doesn't change anything, but for the second operator, it will change. The operator, the conjugation here, all it does is basically shift j minus 3 by 1, or by 1 over h bar, sorry. And what it gives is that it gives rise to a linear term. H bar squared term here stays the same, but then you have a linear term. And the constraints you're going to get are for these particular values of k here. Okay, so if you looked at the original constraints, these were not operators that take the form of an array structure. This one was h bar squared. There was no h bar term. But after you do this conjugation, you get precisely the right form. Okay, so this is really just what you're going to get. If you do the steps, you're going to get these differential operators. These, in other words, the action of these differential operators on Z will produce precisely the linear and quadratic loop equations on the area spectral curve. Okay, so there was a question, what's the mode of a field? Yeah, so I guess that you're not ignorant at all. I did not explain that. But the modes of a field, so I mean, you would have to define what well, vertex operator algebra is, but the modes of a field, I mean, the field is going to be a map from the space of states of your vertex operator algebra, which is just some vector space, and to some formal series and some variable where the coefficients of the formal series are endomorphisms of the space of states, basically operators, which is you can represent as differential operators, and this is what we call the modes. So the modes are the coefficients of the field. The field is a formal expansion, and the coefficients here are called the modes. Oh, sorry, that might not be very clear because I haven't defined VOAs whatsoever. But yeah, that's for our point of view, these are just differential operators. But that's where they come from. That's what the words mean. Okay, but why does that matter? Well, the whole point here is that from this construction here, it follows directly that this condition is satisfied. Why? Well, it turns out that this condition is always satisfied if your operators are modes of a W algebra. Or at least not quite. I mean, you have to classify the subalgebras of modes such that this condition is satisfied, but we've done that in a paper, and in particular, this case is one of them. So basically, the W algebra have some structures. I mean, the simplest example of W algebra is the Virazzo algebra, which is W of SL2. And in that case, we know that this condition is satisfied because of the commutation relation between the modes of the Virazzo algebra, the LM, right, which would be the modes of the W algebra here. And for general W algebras, the commutation relations are much more complicated. But this condition here, you can get just by studying the W algebra itself. So the fact that you end up with a representation of WGL2 is what tells you that this is satisfied, and you don't actually have to prove it. This follows from the property of W. So that's kind of cool. That's very cool. And that proves that you have an area structure. What's cool too is that these are very similar to what you've seen before. These are the constraints I just wrote are essentially the Kontsevich-Witten-Virasol constraints. And this is basically what it says on one way to see why, if you calculate the correlators on the area spectral curve, you get intersection numbers for MGN bars, because really topological recursion on the spectral curve, the area spectral curve, is exactly the same as it's just a reformulation of the Kontsevich-Witten-Virasol constraints. And why? Well, if you look at these two operators I had, so I had two sets of operators, so it was slightly different from the Kontsevich-Witten, but the first set of operators were just these operators. So J2K are just derivatives with respect to the even variables. So what this says is that Z does not depend on even variables. So in other words, the FGNs, where you have 1 and 3 being even, are always 0. Right? So that also explains my weird way of introducing the Virasol constraints, where I keep only odd variables. Was unnatural. That's not what Witten did originally. But from our point of view, this is what you get, because the first constraint, the linear loop equation, translates into the statement that it does not depend on the even variables, but in principle, they would have been there. And then H2K, once you reduce, so in other words, if you get rid of the even variable, then you see that the operators I just wrote are precisely the Kontsevich-Witten-Virasol operators. Okay, so you get exactly the Virasol constraints. And this reduction here is really just going from WGL2 to WSL2, if you know what these things are. That's all we're doing here by getting rid of the linear constraint. Okay, so anyway, what did we get here? So what we got is that the loop equation plus the projection property, if you do that on the area spectral curve, on the one hand, you get the Kontsevich-Witten-Virasol constraints. This is the area structure construction. On the other hand, you get topological recursion on the area spectrum. And now we know that the two are the same, because they are both constructing the unique solution of the loop equation that satisfies the projection. That's the bridge between the two constructions. And that explains why they're both calculating intersection numbers. It's the same FGNs. That's why I use the same letter. Okay, but that's just the area spectrum. That's the standard, simplest possible case. But you can do the exact same construction much more generally. And you can just do it. Again, the Bessel case is the next case. And it's very easy to do explicitly, not very easy, but it's possible to do it very explicitly too, just like the area case. Good exercise. If you construct the operator, you'll see that you get almost the same operators. What you'll get is the same W's, but now the conjugation is different. So instead of conjugating by J3, third mode, so del3, shifting x3, then what you conjugate with is J1, derivative with respect to the first variable. Again, why is that the case is just a calculation. So this would be, this doesn't change the first one, but the second one, all it would do is add a different linear term. And this would be the same. And the only difference is that the second constraint here start only at k equals to 0, not k equals to -1. This was coming from the fact that the loop equations, the quadratic loop equations for the Bessel case, had one less constraint, two less constraint if you want, because it was starting, it could have a double pole instead of being holomorphic. So it was less constraining. Okay, but now if you remember, this is just the BGW-Virasol constraints. Again, it's not quite the same because of this term, but this term only says that Z does not depend on the even variables, so you can get rid of it and get rid of the even variables, and then you recover precisely the BGW-Virasol constraints, which is beautiful. So again, it's the same loop equation plus projection. in the case of Bessel spectral curve on the one and gives topological recursion on Bessel. This is just formal manipulations and then solving the loop equations. On the other hand, gives you BGW Virasol constraints, which is the area structure reformulation of the recursive system. Okay, and then you can just do the general case. And in general, it's actually not too hard. So before doing fully general, let me just connect with some of the examples we saw before. So suppose we're still imposing one ramification point, simple, and we're not changing omega 02. So this was the case that was a generating series for kappa classes. So intersection number of psi and kappa classes, right? So I had that omega 01 was equal to z squared plus sum of gk z2k plus 2 dz, and omega 02 was the standard one, and x was 1/2 z squared. Well, all you're going to do here is quite simple. So you just conjugate. It's always the same thing, but just a different conjugation, because all you're doing is omega 01, and this is exactly what this conjugation thing was. So I'm going to define a T operator, which is defined in terms of the theta of omega 01. Remember, the F01 are just the coefficients of the expansion in Z in this case, because the C's are just the powers of Z. And then the operators that you're going to get are just the conjugation of the same WIK. So it's always a representation of the same W of GL2, or Virasol, if you want, after reduction. Okay, and these T, if you know about co-T, cohomological field theories, these are related to the Giventhal translation operators and the reconstruction formula for semi-simple cohomological field theories. But if you don't know about that, that doesn't mean anything. But if you do that explicitly, you'll see that H1K is always the same. And all you're changing is the linear term here. So all you get is something like that, some sum here, some GN, J2K plus 2N plus or minus plus 3. And then the quadratic term remains the same. So you're not changing commutation relations, so the ideal condition is always satisfied, but you're changing the linear term. So this is not just h bar times the derivative, but you can find a combination. You can find linear combinations of those that will be diagonalized. So in other words, you can diagonalize these things so that they take the form of area structure. So that is an area structure, and that's great. That's what you get. Okay, so it's very simple. Now, if you change omega 02, then you will introduce more term in your conjugation, but it will still be just conjugation of the same W's. And that's true for any ramification point that's simple. You just conjugate the W's. That's all you have to do. Okay, so the general picture here, so for any spectral curve with ramification points r equals to 2, what you get, what is topological recursion? Topological recursion is very simple. This is my spectral curve. You have a bunch of ramification points. All you do is that to each ramification point, you attach a copy of W of GL2, or if you want, Virasol, which roughly speaking is the same after reduction from GL2 to SL2. And these are either, basically what you do is that you assign either Kontsevich-Witten or BGW constraints. Same here for each ramification point, depending on whether it's area or Pascal. But of course, these representations, these operators you get are quite complicated because they are conjugated by the data of omega 01 and omega 02. So they look very complicated, but really they're just a bunch of Virasol constraints. So topological recursion really is just Virasol constraints locally at the ramification points. And that's something that was not appreciated, I think, in the early days of topological recursion, because the formula is kind of weird. But if you rephrase it as area structures, you just get a bunch of Virasol constraints. I think that's kind of cool. But yeah, so that's basically what happens. And then I can tell you what happens for general R, because this is the best way, I think, to understand what happens for general R. So for R equals to 2, the picture is the same. But now each ramification point comes with a ramification order, which doesn't have to be 2. And all that you do is that you assign to each of those a representation of GL, W of GL R. So R1 for the first one, Rn for the last one, and so on. And these representations, again, are complicated because you conjugate with the data of the spectral curve, so omega 01 and omega 02. But basically, topological recursion for higher ramification is just a bunch of copy of W constraints. So if you know about W algebras, this is where it comes from. And if you take, this is where the formulation for topological recursion for higher R come from. And if you take, for example, this case, then these constraints are just the Witten R spin W constraints. And if you take other S's, then there are different constraints. But that's basically what you get. And that's a beautiful picture. Okay, this was basically, this picture was mostly explored in that paper originally that I've mentioned a number of times. And since then, it's been explored or developed in a few more papers of various authors. Okay, so that is pretty much all I want to say. So I'm going to end with just a last comment on what I wanted to talk about today. So what I want to say is that this is not just a reformulation. So what we've done so far is the following, right? So what we did is that the central, I would say, statement of all this business is the loop equations and the projection property. Okay, so this was our starting point in this lecture today. And then we showed that you can reformulate it in 2 different ways. The first thing we did is to show that if there exists a solution, then it is uniquely given by topological recursion. This is important. If there exists a solution, because what I've done is show you that if you start with the loop equations through whatever 3 or 4 steps that I showed you, you can basically obtain topological recursion. But that is if there exists a system of correlators that satisfies the loop equation in the first place. So the equivalent question here is if you start with topological recursion, doesn't construct symmetric differentials, which I mentioned before. And for general loop equations, the case where R is greater than 2, we don't know a priori whether there exists a solution satisfying the projection property. So this is, it is proven for R equals 2, but for general R, we wouldn't know. Okay, so this kind of connection here is only assuming existence. On the other hand, the last part of the lecture today was reformulating these loop equations plus projection property as W of GLR constraints or area structure. I mean, more precisely, it would be a bunch of copies of W of GLR, 1 R for each ramification point. And because of the structure of W algebra, we know it's an area structure. So we know that the commutation relations of the ideal is within H bar squared I. Okay, so this is very non-trivial because then that implies that there exists always a unique solution Z to the constraints. Okay, and the statement here is not only uniqueness, it's existence as well. Okay, so the reformulation here is just a reformulation. So what this shows here is that it proves existence. So it proves that actually there exists a solution. And that's a very non-trivial statement. And as far as I know, for R greater than 2, this is the only way that's known right now how to prove that there exists a solution. So how to prove that topological recursion produces symmetric differentials. So this is, in a sense, a proof that TR produces symmetric differentials, which is a theorem I mentioned before. And this is essentially the proof. This is a reformulation as W structures. So it produces symmetric differentials or correlators, but that's, if you assume that the spectral curve is admissible, and this is in fact the origin of the admissibility condition. As I said before, this was not expected, but once you reformulate as area structures, as WGLR constraints, you realize that you need to impose admissibility, otherwise you wouldn't get an area structure, and there would be no solution. So that's really the essence of the proof. All right, so that's pretty much it. So this is the bridge between the two constructions. What you can see here is that topological recursion provides a large class of area structures, array structures are more general. There are many array structures that don't take the form of representations of WGLR, so they're not necessarily given by topological recursion. There's been a lot of work on that, so you can construct a lot of array structures as representations of other algebras. Usually you want to construct them as representations of some sort of algebra, W algebra, otherwise it'd be very hard to prove the ideal condition. But you can, there's W algebras for other D algebras, not just GLR, so you can do SO2N, whatever, and you can construct array structures in this way. Now you could say, well, what is the analog of topological recursion? In some cases it's been constructed, you can kind of rephrase these other type of array structures as some sort of recursive system on a spectral curve. It is more complicated. You can explore that. You can go way beyond what I've just presented here, but that is the starting point, and that's I think a beautiful story. Okay, so I'm going to end here for today. We have time for questions, and then next lecture we'll just talk about a bunch of applications of this whole framework.